Okay, let's first review what we learned last week. Last week we learned the serial communications, and especially in the serial communications, there are two parts. First part is how to control, how to configure the serial communication hardware block, and second part is that how to set the baud rate. Okay, that's two different parts. First part, where you control or configure the hardware blocks, you need to configure or you need to set a certain value into register called SCON, serial control block. Okay, remember that there was a register called SCON. So in the SCON, you basically configure such as you need to set the mode of serial communications. There are 4 different modes, right? Mode 0, mode 1, 2, 3. So depending on the mode, you want to set it like SM0, SM1 bit, those 2 first bits, right? So you need to set the serial communication in order to run the serial communication hardware. There's also one bit called the REN, receive enable. Okay, in order to receive a certain bits, okay, you need to enable the receiver block. So by doing this, by setting the value into SCON register, you basically enable the receiver and also configure the mode or set the mode of the serial communication hardware block. However, in order to run the serial communication block, you need to set the baud rate. Why do you need to set the baud rate? Why do you need to set the baud rate? So baud rate basically means that the speed, how many bits you're transmitting. Okay, like a 1200 bps per second, for example, like this, right? There are so many different value, 1200, 2400. There are so many different BPS. So you need to set the BPS. Why do you need that? No? Because this communication is asynchronous communications, right? Remember that among those 4 different communication modes, right? Serial communication modes, mode 0 was a synchronous communications. Remember? The synchronous communications, you have a clock, right? You have a clock pin. So therefore, depending on the clock speed, your communication speed is decided. If you have a fast clock, then your communication speed, BPS, is based on the clock. But you are transmitting the clock. So so if you want to make a 1200 BPS, then you can make the clock based on this speed. If you want to make a faster transmission, then you can make a clock based on the faster clock. So it's up to you, because you make a clock, right? And you transmit. However, and also the receive, right? From the receiver point of view, the receiver is receiving the clock. So by just simply looking at the clock, you can actually decode. You can recover the bits. Okay? So therefore, transmitter receiver doesn't have to agree with a certain BPS. They don't know. Initially, they don't need to know. Okay? Because you need a clock. You have a clock. However, in asynchronous communications, you have no clock pin. There's no clock. So the receiver and transmitter, they do not know what speed. Actually, receiver doesn't know anything. Receiver doesn't know what speed the transmitter is transmitting. But without knowing the BPS, we have some problem. What kind of problem do we have? Remember the example that I showed you? Transmitter maybe is transmitting 110011. Okay? Maybe transmitter wants to do that. But the receiver maybe is confused, because maybe receiver thinks that 101, right? Maybe that's what receiver is understanding. So that's a misunderstanding, right? So that happened. Therefore, the receiver and transmitter, initially, they need to agree. Okay, we are going to make communications based on this speed. Initially they agree with a certain speed. That's a baud rate. So therefore, in order to do asynchronous communications, you need to set baud rate. That's what we are talking about here. Okay? Because this is asynchronous communication, we need to set the baud rate. So based on the baud rate, such as 1200 bps, the transmitter is transmitting 1200 bits per second, and receiver is expecting this speed. Now then, the problem is that how do you this basically means that one bit duration is almost like 800 microsecond, right? It's almost 8,000 bps means that one bit is 1 millisecond, right? 1,000 bits means one bit 1 millisecond, but it's 1200 bps. Therefore, one bit is almost like 800 microsecond. So how do you know? Transmitter also need to know, and also the receiver needs to know the bit duration. Okay, both transmitter and receiver needs to know the bit duration of 800 microsecond. But how do you know 800 microsecond? So that's why we need a timer. Transmitter is running the timer and measure the 800 microsecond. Receiver also, they need to run the timer in order to measure the 800 microsecond. That's the only way that I can know the 800 microsecond bit duration. Right? That's why we need a timer. So in order to set the baud rate, we need a timer. But we need to set this one to run the asynchronous communications. So it's all related, right? So this is a hardware logic. This part is a timer. Okay, we have a timer hardware here. In timer hardware, what you need to do is that you need to set what timer mode you want to run it. So there are 4 different modes, right? Mode 0 to mode 3 in timer. Especially in timer, you want to run this timer with a mode 2. Why is that? Because mode 2 timer has a very nice feature called auto load, right? Auto reload. So what you need to do is that you need to set the initial value for the timer and then run with a mode 2, right? Then whenever the overflow happens, then it's auto reload, right? The initial value is loaded and then run. Overflow, then again the initial value will be loaded and run. So auto load. Hardware does do all these things automatically. That's why it is very convenient. So we use this timer 1 with the mode 2, timer mode 2, right? Then this timer hardware will give the overflow in every certain second, every certain delay. So how much delay we have every overflow, that is based on the initial value we program. Okay? So every time you get overflow, every often you get overflow, then inside this hardware block, you have this bit, right? Where is this bit? This particular bit is in the register called PCON. Okay? That particular bit, only this bit. This particular bit is related to the serial communication block, but that bit is not in SCON, but that is in PCON, another register. Okay? So you need to set this bit, either 0 or 1. So if you set this bit to 0, that means our hardware is connected to this. So therefore, we are using this hardware. And when you use this hardware, now the timer is running. Every often you have overflow, right? First overflow, second, third, and every time number of overflows become 32, now you have a 1 clock coming out. Okay, so 1, 2, 3. There are so many overflow coming, and 32 overflow comes in, then you have a 1 comes out. So therefore, maybe as an example, right? If you have overflow in every 1 millisecond, you have a 1 overflow. Next millisecond, you have another overflow. Every millisecond, you have overflow. Then, what is the duration that you have a signal coming out from here? This is 32 milliseconds. Okay? Every 32 milliseconds, you have a signal coming out here. Right? And that signal coming out is going to be your baud rate clock. And this baud rate clock is the speed that you want. And especially as an example, right? Let's see that in our example, we want to use 1200 BPS. Suppose that we want to use this baud rate. This baud rate, as I said earlier, it's like 800 microsecond. So you want to have 800 microsecond right here. Right? You want to have 800 microsecond. So you want to get the 1 clock every 800 microsecond. So right here is going to be very slow clock, and 1 clock is 800 microsecond. So in order to get the 800 microsecond here, right here, at the input of this block, how much delay do you need for every overflow? 800 divided by 32, right? So that's what you need. Because you do the divide by 32, so you have a slower clock right here. But this clock, eventually, we want to have 800 microsecond. So therefore, right here, we want to have how much? It's like a 3 or something, right? 30? 3? 800 divided by 32. It's like 3 almost, right? Microsecond. So that's the delay that you want to have in this timer. Then now, what you want to decide eventually is that what initial value do you need for the timer? That's what you need to decide, right? What do you need? For here, the purpose of this timer is to create a delay of 3 microsecond. So once we have a 3 microsecond of delay right here, then you're going to have 800 microsecond here. You understand what I'm saying? So that's what's happening here. So to do that, mathematically, we can calculate it this way. The reason that we do the 256 minus something is because that 256 is the maximum value that TH1 register can have, and you want to set a certain value in order to make it overflow when this many clocks comes into the timer, right? And you have a system frequency which is 12 megahertz, and you divide by 12, because if you remember the timer inside, first of all you use an internal timer. If you look at the timer, there's an internal clock. In the internal clock, you divide by 12. Remember, right? So that's why we have a 12 right here. Okay, so let me remind you. Here we have a system clock or system frequency. Generally, we are using as 12 megahertz. Inside the hardware, we have divided by 12. So therefore, 12 megahertz divided by 2, we're going to have a 1 megahertz clock right here. And this 1 megahertz clock now goes to the timer, and we have a TL1, for example. That's the register in the timer 1, right? And now, when you run the timer with a mode 2, then mode 2 has auto reload feature. What that means is initial value, you want to program it here. Then whenever this timer runs, this initial value will be auto reloaded into here, okay? Because that's initial value that is copied into here, and then run it. And every time you get a clock, 1 megahertz clock, then the value inside here is incremented like a counter. Okay? And every time this value, this is 8 bits, right? So you have a 1111, 1111, and then next clock comes in, then it becomes a 0, then you have an overflow, timer overflow. How do you know in timer overflow? You have a TF1 bit, right? TF1 bit becomes 1. That means timer has overflowed. When timer overflow happens, this signal, TF1 becomes 1, that comes in here. Okay? When this comes in here, this one actually, just to help you to understand that this block that shows you as a division of 32. But inside here, actually, if you look at the hardware inside, this is another counter. Okay, this one is another counter. What counter is this? This one actually, if I look at inside here, that is the same as that is like this kind of counter. So this one, inside here, you have a counter with the initial value 224. So whenever you get a clock coming in here, that particular clock actually is overflow. So whenever you have an overflow clock comes in, this counter, again, this is same as a counter. This counter is incremented. Okay? And every time when you have overflow clock comes in, then this clock, this counter value, this value is incremented. Eventually, overflow comes in here. Eventually, when you have a 32 overflow clocks comes in, then this becomes 256. Right? Meaning, what is 256? All zero. It's all zero. So this counter actually has now overflow. That's how you detect that overflow. When you have when this counter has overflow, that's the time now you have output. Okay? Before that, you have no output. So that's how you do this division. So this division actually same, exactly same as a counter. So we are actually have multiple counters here, right? Many counters in many different places. This one is actually counter. So when you have a 1 overflow, 2 overflow, 3 overflow, nothing happens. When you have a 32 overflow, then that's the time that you have an output. Once you have an output, this counter will be reset. Again, then 1 overflow, 2 overflow, nothing happens. And when you have a 32 overflow again, then you again get some signal out, right? Some clock out. So that's how things work here. So the output clock rate here is 32 times slower than this one, right? This one you have 32. Now you have a 32 input. Now after you get a 32 input, you get 1 output. You have another 32 input. Now you have 1 output, right? This is 32 times slower right here. That's how things work. Actually, yeah, let me draw it here. So this is a simply speaking, this is the hardware. So we have a original system clock, 12 megahertz, divided by 2, making 1 megahertz clock. And this 1 megahertz clock goes into the timer. Right here is actually timer hardware. So inside the timer hardware, we are getting the input of a 1 megahertz clock. This 1 megahertz clock is coming into the timer as an input. And based on the initial value you program, okay, based on the initial value, whenever this timer overflows, then you get output. And this output now goes into this hardware, which is this hardware, okay, divided by 32 hardware. Inside this hardware, again, there is a counter. So whenever you have a 32 overflows, now you get a 1 output. That's the baud rate that we want. This is the output we want. And how much baud rate we want? For example, this one, 1200 bps. This is a one example, okay? So this is the rate that we want. So based on this, now what we want to try to find out is that from this, we want to go all the way back. We want to go from here to all the way back to find out what initial value we need to program in here, in hot timer, right? That's what we are trying to find out. But since we have a division of 32, 12, and division of 32 here, that's why you have a 12 divided by 12 divided by 32. And this system frequency actually is this one, right? 12 megahertz. So this one goes here, divided by 12, divided by 32. Why do we do divide by 12 and divide by 32? Because this clock is 12 megahertz, but that's being slowed down to 1 megahertz and gets again slowed down by 32. So here actually it's very slow compared to this one, much slower. This much slower, right? So that's what we have here. So mathematically, this is how you calculate it. So simply, as an example, if you want to have a 1200 BPS, if we want to 1200 BPS baud rate, then put this 1200 BPS right here. And since we use 12 megahertz system clock, put that in here, and simply calculate this one, we get 230. So this 230 is the value that you want to program it here, 230. That's what you want to do. Okay? Yeah, so this table basically shows you examples how to set these things and what initial value you need depending on the baud rate. So in the previous slide, we looked at the example of a 1200 BPS, but maybe you want to increase the speed, right? Maybe you want to use 2400 and 9600, right? You want to increase the speed, or even million BPS. If you want to increase the speed, then you need to actually change the initial value. But in this case, right? Let's say for 12 BPS, you have a 230 for the timer initial value. But let's say 2400 speed, it's faster, 2 times faster, twice faster. You need to set this value for the timer. And actually, this one is actually higher value. Why is that? In order to get 12 BPS here, I programmed the 230. But instead, if I want to have a 2400 BPS, then I program initial value I used 243. Okay, this is the initial value that I want to use to get the 2400. Why is that? I'm sorry? The duration. Yeah, because you want to make the overflow faster, right? You want to get the overflow faster. So if you have let's say if you have a 230 as an initial value, then when do you have overflow? This one becomes 256. That's the time you have an overflow signal. And between these, you have a 26. So you need to get the 26 clocks. 1, 2, 3, 4, 26 clocks. Then you have a timer overflow. But if you use the initial value of the 243, then the difference between these is like only 13. So when you have a 13 clocks, then you get overflow. So therefore, this overflow is now 2 times faster, twice faster. Therefore, everything else is twice faster. Right? Let's say I want to have a 9600. Then, of course, you need to make it even higher, 256, 3. In that case, what happens is you're gonna get the overflow every 3 clocks, every 3 input clocks, right? Because this is initial value, 256 minus 253, it's only 3. So you program it 253 here. So every time you get 3 clocks coming in, you get overflow. 3 overflow, something like this, right? Let's say I want to make it even higher. I don't want to have a 9600. Maybe for me it's too slow. Okay? It's a 19,200. Let's say I want to have a baud rate this one. In that case, you want to increase this one even higher, but this value cannot be higher than 256. So we have to do it different way. The different way is that now you see the S mode needs to be now changed to 1. What happened when you set the S mode to 1 is that in hardware, now we are switching to that one. So you are using this hardware. And in this hardware, we are actually dividing by 16. So here, right here, instead of divide by 32, now we are using divide by 16. So therefore, as I said, right, this is the same as a counter. So inside this counter, we no longer has this initial value for the counter. The initial value for this particular counter is now going to be this one. So 240. This is going to be initial value for this particular counter. That way, now you have a 16 overflow, you have 1 output. 16 overflow, you have 1 output. Okay? So therefore, we can make it run faster. So far, what this table basically shows you is that if you change the value, this value, what is this value? This is a timer initial value. Right here, initial value for the timer. If you change this value, okay, let's say if you increase this value, 230, 30, 243, 253. So if you increase this value, then what happens? When you increase this timer initial value, increase it, then you're going to have an overflow a little bit faster, right? You get the overflow faster than before. But if you change the S mode from 0 to 1, okay, instead of 0, if you use S mode equal to 1, then what is it? We are actually using different hardware. Instead of divide by 32, you want to use divide by 16. Okay? So we are using different hardware now. Okay? So by combining these, you can actually have you can use a different baud rate. So this is an example, simple example of setting the 1200 BPS. The clear SM0, set B SM1, this simply basically means that you want to set the serial communication mode. Make it 0, make it 1. So 0, 1 means I want to run the serial communication with the mode 1. T mode, I want to set it 20H. TH1, set it to 230. What is this do? The first, this line, they set the timer mode. Okay, I want to run the timer with the mode 2. That's what this means. The third line, third instruction. And the fourth instruction, TH1, 230, this basically means I want to set the initial value for the timer. Okay, once you set the timer mode to mode 2, and also set the initial value for the timer, then now you can run the timer by setting this one, set B TR1. Okay, once you do that, then now the timer is running. Timer hardware is running. So timer is now running. So every time the timer gets the 26 input clocks, then it gets overflow. Okay, and then what is this one? Move S buff A. This one basically means that whatever value you have A, you copy it into SBUF, meaning you are transmitting. Let's look at an example here. So let's see. Start from the basic. This one, what do you call this one? This is a reset vector, right? Remember that reset vector? So whenever you reset the hardware, we always start from 0, 0, 0, 0, right? So that's why we call this one as a reset vector. In reset vector, you always has a jump to your own program. So same here, in the reset vector, I have a jump start. Okay, so when you reset it, now it suddenly jumps to start, and my start is here. So my program actually starts from here. So let's see. In my program, how I start is that I set the SM0 to 0, SM1 to 1. So by these two instructions, what I do is that I set the serial communication mode to mode 1. And with the next two lines, what I do is that I configure the timer by setting the timer mode to 2, and also I set the timer initial value. And the next line, set P TR1, I run the timer. So once you execute this line, then now your timer is running. Once your timer is running, and then what I do next lines is that I just simply copy it into this memory 40 to memory 43H. I copy A, B, C, and 0. This value, I put it into the memory. Okay, and the 40H copy again into the R0, and call the subroutine, send the text. So now, since we have a call send text, let's jump to send text right here. So let's see what we do in send text. First of all, we use indirect addressing, right? So R0 actually has the value of 40. So let's go to the 40 and read that value. And what do you have in 40? You have A. So read the value A, alphabet A, small a, and copy that into accumulator. That's what we do, right? And JZ finish. If accumulator value inside the value inside the accumulator is 0, then we need to jump to finish. But actually we have the alphabet A in the accumulator, so we just pass. And that value, the alphabet A, now we want to copy that into SBUF. Once you copy it, then what happened? That value is now going over and transmitted over the serial communications. So that's all done by hardware. So what we do in the software is that just do this. That's it. We don't have to do anything. But you copy that into SBUF, and then you want to transmit alphabet A, but that's not the end, right? What we want to do next to it is that we want to also transmit alphabet B. So to do that, what we need to do is that we have to check the TI bit. Remember that? When the hardware, from the software point of view, what we need to do is this one. We want to copy the alphabet A into SBUF register. That's it for the software. But once you do that, then hardware basically gets the alphabet A and read it from the SBUF and transmit. That's all done by hardware. When that actually takes some time. So hardware finishes the transmission of alphabet A. Now the hardware will set the TI bit to 1. So from the software point of view, we need to wait until the TI becomes 1. So that's what we do here. We just wait. What was the dollar? Dollar means it jumps to its own. It's addressing. It's like a label. Same label, but that label is for its own. So you just jump to, you're just doing loop back inside of its own until the TI becomes 1. And once the TI becomes 1, that means the hardware already finished transmitting the letter A. So now it's time to transmit the next letter, B. So first thing to do, TI bit needs to be 0. Okay? You need to clear the TI bit. And then jump, send the text. Jump back. But before that, actually, now you want to read the next letter, and next letter actually is in the next address. So what do you need to do? You need to increment the address. So to do that, you are incrementing R0. This part, this address, this instruction, you can do it here, no problem. You can do it here, it's okay. I mean, it doesn't matter, right? So, but before jump, you want to do it, okay? So that's what we do. So incrementing R0 and come back here. Now the R0 becomes 41. So read the 41, which is alphabet B, and you do it again. And increment it again. Now at 42, you read the C. And again, transmit it. Then again, it's incremented. It becomes 43. Now the 43, R0 becomes 43, and jump back here. And you read the 43. And actually, 43, we have a value 0. So now, eventually, when R0 was 43, accumulator has the value 0. Then, on the next line here, we actually have a condition here. So, accumulator is 0. So, suddenly, we need to jump to finish. Finish is right here. Return. So, therefore, you are going to return. We return to here, end. So, the program is end. So in this program, this is just transmitting three different letters. Okay? A, B, C. Alphabet A, B, C. That's what we do. Okay? So transmitting, simply. And in this particular program, what we do is that we are using the serial communication hardware, of course, because we are transmitting. In addition to that, in order to set a certain BPS, in order to make it 9600 BPS, we are using timer. See here, we are using timer, right? We are using timer hardware. We are also using a serial communication hardware, but we are not using interrupt. In here, we are not using interrupt, right? We don't need any interrupt right here. Let's look at example 2. In example 2, right here, again, we have a reset vector, jump, start. So let's jump to start here. This is where my program starts. In my program, first of all, I set my port 1 into FFH. And then next 2 lines, I set the timer, similar way. Okay, configure the timer. And also the next line, you see that move SCON 50H. So this is the configured serial communication block. And next one line, I have a move IE 9H. This one, what is this one? IE. What is IE? Interrupt enable. So in this particular program, I'm going to use interrupt. Okay, since I enabled interrupt, I'm going to use it. 9H means that it's, what is 9? 9 is 1001. In order to use interrupt, you need to set the 2 bits. One bit is global interrupt, which is the very first bit. And you also have to set the interrupt that you want to use, right? So in this particular case, we want to use a serial communication interrupt. So therefore, you have to turn on the global interrupt. You have to set the global interrupt, and also you have to set the serial communication interrupt. So therefore, we have a 9H, 90H. Okay? So you need to set this way in order to use the interrupt. And then you run the timer, set BTR1. So timer is now running. Timer hardware is now running. And then right here, you read the P1, port 1, and copy it into A. And the value in A, you copy it into SBUF. So you want to transmit. And SJump, loop, meaning that you jump back. So you are basically looping here. Okay? What you are doing in this looping is that you are simply transmitting the value in the port 1. Port 1, you may have some value. Initially, we initialized the port 1 with FFH. So maybe if nothing happens in port 1, then maybe P1 still has the same value FF. In that case, you just keep transmitting FF. Only transmitting FF, right? Because we are doing loop. In this case, it's like a infinite loop, right? You just keep transmitting. However, the thing that you need to remember is that we are actually looping here, infinite looping, but we actually enabled interrupt. So when you loop, right, what can happen is that someone may be transmitting a data to you, maybe some letter A, okay? Maybe someone else is transmitting a letter A to you. Then when you receive a certain letter, then normally you are looping here. But when you receive some information, receive some byte, first of all, the hardware receive it, right? The received letter comes to the hardware, and the hardware will copy the received byte into SBUF. Okay, that's what the hardware does. So hardware is receiving this is our processor, and we have a serial communication block. Inside this serial communication block, we have SBUF register, and in our processor, we have pin called the receiver, right? The RxD pin, and in this pin, you have it is connected with the let's say PC, and let's say in PC, we are transmitting letter A. Like this, right? This letter A goes over here, and the hardware block, this hardware block basically receives this and copy this value into SBUF, like this, right? This value now should go to this one. But this copying the value here into this one takes time because this line is a serial line. So this A maybe in ASCII mode, maybe this is like 1101, 1111 maybe. And this one, this information is now packetized, right? Remember that we have a start bit, stop bit, okay? In order to transmit 8 bits, you need to have a start bit, and then you have an 8 bit, and you have a 8-bit and stop bit here. This kind of information is right here in this line, right? In this line, we have this information. So inside the hardware, the serial communication hardware, what they need to do is first to detect the start bit, right? We need to detect the start bit. So once you detect the start bit, then this hardware, receive hardware, will decode 8 different bits, right? That's all done by the hardware. So this kind of thing takes some time. It's not instantaneous. It probably takes some time. And once this decoding is all done, then this 8 bits now goes to this SBUF. Once this bit successfully is going to SBUF, now then RI bit becomes 1. Okay? Once this 8 bits goes into SBUF, then RI bit equal to 1. And only then software now knows. Before then, software doesn't know anything. Only the hardware detects the start bit. So detecting the start bit, stop bit, all these things is hardware. Software is nothing to do with this, right? Software never see this. So hardware do all these things and then copy this value in here in the SBUF. And after that, RI becomes 1, and software now realize that there is a new value arrived. Okay, new value arrived in here. And that's the time that you get an interrupt. Because RI equal to 1, now we get an interrupt. Normally, normally you are doing loop, but suddenly when the Ri becomes 1, you get an interrupt. When you get an interrupt, what happens? In normal case, you are looping, but you get an interrupt, so you need to jump to interrupt vector. We have an interrupt vector right here. Okay? The interrupt vector for serial communication is 23H. So because of an interrupt happens, you suddenly jump to here, and we have an interrupt vector jump serial. So now let's jump to serial, which is right here. So this is our interrupt service routine. Okay? So let's jump in here, and this is interrupt service routine. And first of all, in interrupt service routine, what we do is that for in serial communication, we have a TI, transmit interrupt, RI, receive interrupt. But the transmit interrupt, you don't have to do anything. Okay, you don't have to do anything. But in receive interrupt, what you need to do is you have to copy the value. Right? So if that was a transmit interrupt, because when you have transmit interrupt, still you can come here. Because when TI equal to 1, still you get an interrupt from the hardware. So you jump in here, and if the TI equal to 1, then you can just jump here and clear the TI, and you can go out. You can return. Because in TI equal to 1, you don't have to do anything. However, if that was RI, then now you move on, and you read the value in SBUF and copy back into A, okay, because you're reading the value A, and move on. Okay, that's what we're trying to do. Okay. Okay. So far, for the last couple of weeks, we learned the interrupt, and we learned the timers, and we also learned the serial communications. Okay, and those are very important. And today and next week, for the next 2 weeks, what I'm trying to show you is the application. Okay, since you're doing the project, okay, course project, you're going to use some of the application, like you're going to use the keyboard, you're going to use the LCD, LED, something like that, right? So what I'm trying to show you is some of the basics or some brief introduction, and show you how to use these kind of devices, external devices with 8051 processor. So first example is a 7-segment. You know 7-segment like this, right? 7-segment. So we have 2 different types for 7-segment. One is a common cathode, and the other is a common anode. And the difference is this one only. If you look at inside, right? Each of these is simple diode. Okay? Each of these simple diode, we have 8 different diode. That's actually what it looks like. You have a diode, and for each of them, you have a 1 ground pin, and the other is VCC. Same thing for this one. You have a VCC, and you have a ground. Okay, each of them is independent diode, but we have 8 of them. In common cathode, as you see here, what that means is VCC is connected to I/O pin. What that means is that ground, we always have a ground and VCC, and in here, in the ground pin of this 7-segment is connected with the ground of your board. Okay, ground you don't have to worry about. Ground is already connected as a 0. So for this common cathode, in order to make this one on, what you need to do is that you are connecting a VCC here. Okay, if you put the VCC here, this will be on. Okay, if you want to make this one on, then you are connecting VCC, because ground is already connected. What you need to do is connect the VCC, then it will be on. This one actually is the other way. In common anode, VCC is already connected. So in order to turn this on, what you need to do is you want to connect this one to ground. Then it will be on. Okay? That's the only difference. So that's why maybe I think you are using this one. Because when you write 0, then it will be on, right? Actually, that was the case of your LED, right? When you turn on the LED, set that particular bit to 0, then it is on. 1, it is off, right? That's almost the same as an anode. So if you want to make this on, you want to turn on this diode, you can connect ground in this type. If you want to turn on this diode in this cathode type, you want to connect VCC. So that's the only difference. So in data to program here, if you want to have a 0, let's say I want to have a 0 like this, then you want to turn on this one, this one, this one, this one, this one, this one, right? You want to turn on these 6, then it'll show you as a 0. So to do that, we have actually alphabet here: A, B, C, D, E, F, G. Right? So what you need to turn on is, in order to make a 0, you need to turn on A, B, C, D, E, F, like this: A, B, C, D, E, F. You make it all 0. So this table basically assumes you use the common anode. In the common anode, you write the 0, 0, 0, 0, 0, 0, 0, then it'll show you 0 like this. Okay? Now then, here's how to use it when you have a multiple 7 segments. Let's say sometimes you buy a device like this, and this device has a 4 7 segments, right? But if you look at the pin, we only have 8 pin. Okay, 8 pin: A, B, C, D, E, F, G, D, P. D, P is a point. So you have 8 pin, and also you have another 4 pins. That's it. The problem right here is this one. Actually, going back to this one, in order to turn on this particular 7 segment, you need 8-bit, right? Because sometimes you want to make a 0, then you want to turn on this and this and this one, this one, this one, this one. Maybe you want to make a 3. So depending on what letter, what number you want to have, you want to control each of that, right? So you need the 8 pin because we have 8 diode. You need 8 pin. So if you have 4 7 segments, then this one you need 8 pin. This one you need 8 pin. Another 8 pin, another 8 pin. You need the 8 pin for each of them, right? That way you want to write some number, for example, 2, 3, 1, 5. If you want to do that, then you need to have 8 pin separately. Then we only have 8 pin. Well, we only have one set, one group of 8 pin. Then how can you do this? That's a problem. This 8 pin is connected to all of them. So what happened in this case is that, let's say I turn on A, B, C, D, E, F right here, since we only have one set of 8 pin. If I turn on A, B, C, D, E, F, when you turn on A, B, C, D, F, then what number do you have? 0, right? So you're going to have a 0. But when I have A, B, C, D, E, F, make a 0, then you have a 0, 0, 0, 0. All these 4 numbers will have a same number, because I only have one set. So how can you? But that doesn't make sense, right? I have a 4 segments, so I need to be able to show different numbers. How can you do it, since we have only one? Okay, that's a good point. We have 4 pins right here. So what? How can you do it? There is a trick here. It's a small trick. the trick is that this device is cheating you, cheating your eye. What that means is that here's how things work. We have 4 pins here, right? So 4 pin, each pin is corresponding to each of these 7 segments. First pin is connected to this. Second pin connected to that. Okay? So each of pin is connected to each segment. Now what do you want to do? Let's say I want to display 2315. Okay? Let's say you want to display 2315. In that case, you turn on the first bit. In that case, this 7 segment is now enabled, and you send the 2. Okay? In that case, only this one will show 2. All the other will be disabled, right? So it's black. And right after that, you turn on the second pin. So you turn on the second 7 segment, and then transmit 3. Okay? Then, of course, only the second one will show you 3. However, the trick is that these 2 will stay. Okay? These 2 will be still there. So you have a 3. Same way, you select the third one and transmit 1, then the third 7 segment will show you 1, but 2, 3 is still there. Okay, that's how you do it. That's how you run this one.
But if you do that from leftmost, the LED, then is it possible to turn on the rightmost LED?
Leftmost 7 segment. This one? You mean what?
I mean, if we turn on the leftmost LED by setting on the beat. I mean, by using the beat bottom of the 4 beats, set one of the beats, then I think we can use the leftmost LED. But as you said, we can if you want to use if you want to turn on the second LED, then the first LED, the value of first LED is still there, as you said.
No. Yeah. Okay, I see what you're saying. So when you select the second LED, then this second LED, only this second LED will have a value 1. All the other will have a 0. Okay. Here's what happened. Let's say this is active high, right? So if you have all 1 for all these pin, right? Then what that means is all these 4 7 segments are selected. You don't want to do it, right? If you select all of them and you transmit only 1 value, because at one time you can transmit only 1 value. If you selected all of them, then these all 4 will show you the same value. You don't want that. So you are going to select only 1 at one time. So first of all, initially, you are selecting this one only. So 1 0 0 0, and then transmit value 2. So now the first one show you 2. Right after that, you are only selecting the second one, right? And then transmit 3. Then that 3 value will still there. So it's like a one after another, but still the previous one still there, remains there. That's how you run this one.
And I wonder if I change the order,
change the order is fine. You can change the order. You can start from this one. That's okay. You can first you can select this one and display 5, and then you select this one and display 2, and then this one. The order doesn't matter. The order doesn't matter. But what I'm saying is that you need to do that. It's not automatic. You need to do that, like select this one and write one value, select another one, write another value, things like this, right? That's how that's why maybe some of you can see that when you have a multiple 7 segments here, then sometimes you see that the values are a little bit flickering. Okay, that's why flickering. But anyway, that's how you do it. Okay, that's how you can control. Actually, this picture shows you that, right? You can turn on this first, and then this one, and then this one after another. The order doesn't matter. You can do it reverse order, no problem. Another device, another external device that you can use is a dot matrix. This is a dot matrix. So dot matrix is nothing but a series of LEDs. This is the dot matrix, and this actually is just LEDs, but we have a matrix of LEDs. That's it. And there are so many different types of LEDs, but right here as an example, what I'm showing you is a color. It's a color dot matrix. But this is not a true color. It is only showing 3 different colors. Each LED right here can only display green color and red color. But when you mix the green and red, then it's going to be, we call it an amber color. It's like orange color. Okay? So including that amber color, you can display 3 different colors. Red, green, and mixed of red, green, orange. So each of these dots, you can display 3 colors. Now, however, we want to control each of these LEDs separately, right? Again, this LED is on, maybe next LED we want to make it off. Maybe this one green, that one red. You can control each of them independently. However, even in this case, we only have one 8-pin, another 8-pin, and another 8-pin. We only have 3 pairs of 8 pins. That's it only. So how you can control them? Especially also, right? This 8-pin right here, actually let's look at this one. This 8-pin right here is to select the rows. What is rows? This is a matrix, right? Rows is this line. First row, second row, third row. Okay? So each of these pin is connected to the row. The last pin is connected to the last row. Okay? And these 8 pin right here, these 8 pin, this 8 pin is connected to the color. I think this is red and this is green. So since we have a red color and green color, you have this 8 pin to control the red, this 8 pin to control the green. So how you can display? Let me see. Here's how to do it. Let's say I want to turn on that bit, that LED, and that LED. Let's say I want to turn on these 2 LED. And let's say I want to turn on these 2 LED with red color. In that case, since these 2 dots are on the same row, what I need to do is that using this 8 pin, I need to select the first row. Because that's the row that I want to have, right? So you need to select that row. And using this 8 pin, since I want to have a red color, I use this 8 pin because this 8 pin is for red. And using this 8 pin, these 8 pin are corresponding to these 8 LEDs. So the first bit corresponds to the first LED. The last bit corresponds to the last one. So this one basically selecting the column, this one selecting the row. But this one is for red, this one is for green. So let's say if I want to have this particular LED, that particular LED, only these 2 LED to red, then you're going to select this row, the first row, and you're going to make the second pin and the last second pin to 1. Right? Then only these 2 will be red. But now the thing is that maybe I want to have this pin red on this row, but the second row I want to make another pin to red, another LED to red. Right? However, I cannot select the 2 different rows at the same time, because if I select the 2 rows at the same time, then the same number will go to the 2 rows, so I will have the same colors on the same position. You don't want to do it, right? Because I want to make a different pattern for each row. So that's why, how do you do it? Same way. You basically paint it first row first and the second row. third row, one by one. Like what we did in 7 segment, right? In 7 segment, you have 4 7 segments. You turn on the first one, and the second one, third one. Same way here. First row first, second row, third row, one by one. If I want to have this color, this picture, for example, right? On the first row, this one is red, amber, green. On the second row, I want to shift it. Okay, this red, amber, green. Something like this, right? What do you need to do? First of all, if you look at here, the first row and the last row actually has the same pattern. So first thing to do is that I can select these two at the same time. Because these two have the same pattern, I can select at the same time. So these two rows I selected. Okay? And then for the green color, I want to have this one to be 1. These 2 bits, I want to have a 1 for the green. For the red, I want to have these 2 bits to be 1. So for this particular pin right here, for amber, red is 1, green is also 1. Both red and green is 1. That's how this is mixed. That's how you turn on. After that, now you are selecting second row, last second row. Okay, second last row here. You are selecting these 2 rows. And then do the same thing. One here for the green, and one here for the red. Okay? And do the same thing. That's what we do here in the program. In this program, that's what we do. Okay? Another popular device that you want to use with the device, with the processor, is the LCD. We have a text LCD, which is more popular, and also there's a graphic LCD. But let's look at the text LCD first. Typically, text LCD looks like this. This one actually has only 2 lines of characters. Sometimes you can see that 4 lines of characters, but it's almost same. So let's think about 2 lines of characters. Here it's a 2 line. In this kind of character, LCDs, concept is similar. In this case, again, what you need to do is that you are writing one value, one character, and the next character, one after another. Okay? You are writing the character one after another. So this is the hardware of the LCD. You have 8-bit of 8-bit port, DB0 to DB7. So using these 8-bit ports, now you are getting the letter. Letter A, letter B, things like this. Right? So at only one time, you are getting only one 8-bit. So that's why, in order to display these letters, the whole thing, you actually have to get them one by one, one after another, one after another. Okay? And for this LCD device, you have some control pins, E, R, W, read, write, and RS. So this is some description about these pins. E means enable, RW, read, write. Sometimes you want to read, sometimes you want to write. Typically, this kind of LCD device is a writing device. You're going to write some value into the LCD. Then this LCD will display. When is the case that you want to read from LCD? Is there any case? Generally, no, right? Generally, from PC point of view, right? PC, this LCD is the same as our display, monitor. Monitor is only the display, output device from the PC point of view, right? Monitor is not an input device. Unless the monitor has a touch screen, the monitor is always is output device. Same here, in LCD is generally output device, so you don't have to read. It's only writing. However, for checking purposes, you may want to read. So you are writing some value, but this LCD for some reason is not displaying. So now you're confused. You know that you write the value, but this one has to display that value. but there's no display. So something must be wrong. So you may want to check. Okay, you write it first, and then you read it out. Okay? And when you read it out, of course, you have to read the value that you wrote already. So if that's not the case, then that's an error. So only for the error checking purposes, sometimes you want to read. Otherwise, in normal cases, you don't read it. Only writing. RS means the data or command. So what this basically means is that normally you're writing the data. Data means this value. The data you want to display, that's data. Normally you're writing data. But sometimes you may want to do it this way. Let's say I wrote some letters like this, but suddenly I want to clear the screen. Clear. Okay? Then how to do it? How can you do it? So clearing the screen. So clear, remove all the letters. That kind of thing is command. Sometimes you want to clear, sometimes you want to maybe clear only one line. Maybe you want to remove only the middle letter. So you may want to do something. Okay? Some special command. That's a command. In that case, you need to make a special character to send to the LCD. Okay? So that type of thing is a command. So by RS pin, you are selecting if this is data or command. And this particular hardware, again, has also the register, like a command register and data register, like this, right? This is a command register, 6400H. This is just the example. So 6400H looks like this. So this register, of course, is defined in the data sheet. Okay? When you buy any electronic devices like this, for example, in LCD, when you buy a text LCD like this, of course, the vendor will give you the data book, okay, called the data sheet, right? When you look at the data sheet, you will see this kind of register and how to use each of the register, right? So you need to know that because that's how the vendor, manufacturer makes this device. So that's how you use it. So these are the commands, for example, right? Sometimes you may want to display clear, so clear out all the display. Come back to home. What that means is maybe you are writing one character by one character, and you are writing somewhere here, and suddenly you want to come back to the home. This is home, right? Come back to this position. So the cursor position, you want to bring it to the home. Sometimes, right? That's what you do here. So display on, off, and cursor shift, and all these things. And actually this one, CG, I think this is graphic RAM, and DD RAM. So this kind of thing is a little bit special mode. I'll show you. And DD actually RAM, this is DD RAM. Inside this hardware, you have a special memory called this RAM, DD RAM, like this. Special memory. And using that special memory, you can actually do several things. For example, right? Inside here, in LCD, there are already font, like alphabet, A, B, C, D, and those fonts are already here. But for some reason, let's say I want to write a French. Okay, French, you know that there are some special characters, right? Alphabet. I'm not sure about the French, but I think in French, there are some characters maybe like this, right? Something like this. Or maybe something like this, right? You have these kind of characters. So normally, maybe in LCD, you cannot have this, maybe. So in that case, what do you need to do? You have to write it. You have to make it. So how do you make it? Using this DD RAM. That's the purpose of this kind of RAM. In normal case, maybe this is not used. But in order to make a special character, you can design your own character using this DD-RAM and CG-RAM, things like this. Okay? So that's the purpose. This example looks like it's a long program, but this assembly program basically shows you how to use the text LCD. Let me skip this example, so big. But you can take a look at it. It's not a big deal. It starts from here, and you prepare some value and copy that into LCD buffer. And every time you copy that LCD buffer, you call the LCD common, which is this one. And this LCD common routine, what they do is that you need to take a certain delay, because here you see that call this D50 microsecond. This thing basically means the delay, because in the LTD device, especially for this kind of thing, you cannot write the value in a very fast pace. This LCD is very slow. I mean, every LCD, this is very slow. So because of that, what you need to do is that you are going to send some letter, and you need to wait a certain period. And how much do you need to wait? That is decided, that is already there in the data sheet. So when you buy this LCD, then you have a specification of that LCD. In that specification, you will find out that how much delay you need to have for each character. Okay? So find out that delay value into the data sheet. But anyway, for every device, every LCD device, you cannot transmit the data, these letters, right after one after another, right? Immediately, right? What we need to do is that you're going to write one value and wait a certain delay, and then write the next one, wait a certain delay. Every time you do, you need a delay. And that delay actually is pretty big. It's like 100 microsecond or tens of microseconds. It's a pretty big delay. But you need to have the delay, because that's how the LCD works. LCD is a very slow device. So that's why you need to, in your program, you need to have a delay routine. Okay? So every time you do, you have a delay, and then you need some protocol. That's what we do here. There's also graphic LCD like this. In graphic LCD, it actually depends on the LCD, but this one actually shows you one example. In this particular LCD, which is 128 by 64 dots, this is actually black and white graphic LCD. So this LCD has left 64 by 64, right 64 by 64. To display a certain graphic here, you definitely has to have a memory. Okay, you need to have a memory for the left part, left half, and right half. You need to have a memory. So for each, and you have a memory like this, and you have a driver for each of them. And right here, of course, you are getting 8-bit for data. You have some reset and chip select pin, things like this. So let me show you how to use this. So in this case, you have a memory, and inside the memory, 1 bit corresponds to 1 pixel. So you have a 128 by 64 pixel. So that's the size of the memory. 1 bit corresponds to 1 pixel, because this is black and white. So here in the graphic LCD, you will have a DDRAM like this. It looks like it's a bit ugly picture, but what it shows you is that this is 8-bit, another 8-bit, another 8-bit, and that's the address. See that page address? You have address. This is a byte address. And you also have this address here. You have an address on the column, address on the row. So by selecting the address, column address, row address, you can actually select each of the pin. For example, right? If I select the column address BA and the row address 41, then actually you are selecting these bits, these 8 bits. Okay? And by setting like 101010, then you can actually have this particular pixel to be black, that particular pixel to be black, something like this. So that's how you can display some graphic. This is a command. In LCD, graphic LCD, you also have a command mode, also have a data mode. So this is the command mode. That's the example. Another example. What I'm showing you here is that something like this. I mean, some simple example. Let's say if you want to display this kind of picture in the graphic LCD, then what you need to do is that each of them actually is a pixel, small grid. This is a pixel. So if you take this first 8-bit, this is first 8-bit. If you look at this first 8-bit, that's going to be, and bring this 8-bit here, it's going to be like 1110010, right? If you read the value, then it's going to be E2H. Take the next 8-bit, bring it here, it's going to be 1111110, right? So this picture actually is that E2, F8, AC, and some other value. It's this picture actually is some series of 8-bit values. And what you need to do is that you are simply writing these values for each of these address into this LCD, then you are displaying this one into LCD. Simply that's what we do. Okay, now let's move on to the next one. Another popular application is a step motor. Okay, step motor. Step motor looks like this. Of course, a step motor is different from your DC motor. In step motor, there are actually different types, many different types. So this is one example. And this picture shows you a simple operation, simple diagram, how to operate these things. But there are 3 different steps how to run the step motor. So this picture shows you a full step example, but let me explain what that means. Inside the motor here, we have 4 magnets. Okay? We have 4 different magnets, but these 4 magnets can be turned on and turned off. Especially for this part, right? You can turn on this magnet and turn off these 3 magnets. Then you have S, N here. So therefore, the middle one, you're going to have N like this. On the next time, now you turn off, you turn on this one. Then suddenly it rotates. On the next time, again, you turn off this one and turn on this one. Then it's rotate. So it's keep rotating because you turn on this one, and this one, this one, this one, then it's turned on like this. Right? Simply, that's how you do it. Especially the nice thing about this step motor is that you can actually turn on exactly the angle that you want, right? You want to make it turn on with a 90 degree or maybe 45 degree. You can make it exactly 45 degree. Okay, you can make it exact circular, exact angle, circular rotation. There's another way, half step. Let's see what that means. In half step, we can start from the same way. These 3 magnets you turn off and you turn on only this one. Then the middle one goes like this, right? And the next time, what you need to do is that you leave this on, you leave this magnet on, and this one you also turn on. You turn on these 2, right? This one was already on, and now you turn on this one. Then it was like this, but now it's rotating half, 45 degree. Because these 2 on, these 2 off, right? Like this. And next time, now you turn off this one. So it's again going like this, right? So in this case, it's like a 45 degree every time. So that's why we call this half step, 45 degree. Okay? So this one basically show you, example how to do that, how to run the step motor. Each step motor may have a register like this, step in A, B, and this one basically tells you that what to enable and what to disable. In this case, right, we have 4 magnets, so therefore each one has one bit. Like this, for example, right? We have 4 bits like this. So if you turn on this one, then you turn on only the first one, right? And when you turn off this one and turn on, then you are now turn on the right one, things like this. So using these 4 bits, now you can control these 4 magnets. Okay, since we have 4 magnets. These 4 bits is like a switch. It's like switch for each magnet. Okay, that's how you can control the step motor. So these examples 1 and 2 shows you how to control the step motor using full step and half step mode. Okay, that's it for today. Okay, any question?